You know that little blue dot, the one pulsing on your phone's map? Have you ever just stared at it and wondered, how in the world does it do that? I mean, how does this little device in your hand know, with such crazy accuracy, exactly where you are on this huge planet? Well, let's get into it, because the answer isn't magic. It's actually one of the coolest, most surprising uses of physics hiding right there in plain sight.
I mean, it really does feel like magic, right? Doesn't matter if you're in the middle of a packed city or, completely off the grid, that little dot is just there. So how does it pull it off? Is it some kind of super advanced map? Well, the secret is something else entirely. And trust me, it's probably not what you're thinking.
Get this. The secret isn't about location at all. It's about time. Yeah, that's right. The whole incredible globe-spanning global positioning system, it's not really trying to find a place. What it's actually doing at its very core is measuring time. And we're talking about a level of precision it's hard to even wrap your head around. You can think of GPS as this giant, unbelievably accurate clock system just floating up there in space.
Okay, so to really get how this works, we've got to look at the core principle behind everything. It's kind of like a race against time, but the prize at the end? It's knowing exactly where you are.
And it all comes down to a super simple formula you probably learned back in school. Distance equals speed times time. It's that simple. Your phone is basically calculating how far away it is from a satellite by knowing two things. First, the speed of the signal, and that's the speed of light, the fastest thing there is. And second, how long it took that signal to get all the way from space down into your hand.
Okay, but here's where things get absolutely wild. Because those signals are moving at the speed of light, any tiny error in timing has massive consequences. I mean, think about this. If the system's clock is off by just 1/1,000,000th of a second, a single microsecond, your location would be off by 300 meters. That's like 3 football fields. You'd think you're on one side of the street when you're actually 3 blocks away. That's how precise this has to be.
So how on earth do you get that kind of ridiculous accuracy? Well, you use something called atomic clocks. Every single GPS satellite up there has one of these on board. And when I say they're precise, they are so accurate they would only lose maybe 1 second over millions of years. This right here, this is the foundation the entire system is built on.
All right, so we've got these incredible clocks telling our phone how far away the satellites are. But just knowing the distance isn't enough, right? That doesn't give you a single point on a map. So to do that, the system uses some really clever geometry.
The method is called Trilateration, and the best way to understand it is to just imagine this. You're standing blindfolded in a big open field. A friend yells out, "Hey, you're exactly 10 meters away from me." Now, you don't know your exact spot, but you know you're somewhere on a perfect circle around them, right? You've already narrowed it down a ton.
Well, GPS does the exact same thing, but in 3D. So the first satellite signal tells your phone it's somewhere on a giant sphere. Then, a second satellite chimes in, and its sphere intersects with the first one. Now you're not on a sphere anymore, you're on a perfect circle where those two spheres meet. A third satellite signal comes in and bam, its sphere cuts that circle at exactly 1 point. That's your 2D location on the map. But the fourth satellite, the fourth one is the real genius of the system. It does 2 things. It figures out your altitude, so you get a full 3D position, and, this is the crucial part, it constantly syncs the cheap, simple clock in your phone with its own hyper-accurate atomic clock. This eliminates any timing errors right on your device. It's brilliant.
Okay, so if you think that's clever, you need to brace yourself for the truly mind-bending part of this whole story. Because the entire GPS system, it would completely fail. I'm talking useless within minutes, if it weren't for a theory that was published decades before the very first satellite ever launched. And that theory? It's Albert Einstein's relativity.
Yeah, this is where it gets wild. You've got 2 of Einstein's most famous theories locked in this constant tug of war. So, on one side, you have special relativity. It says that because the satellites are zipping around the Earth so fast, their clocks actually tick a little bit slower than our clocks down here. But then you've got general relativity, which says that because the satellites are way up high in weaker gravity, their clocks should actually tick a little bit faster. So, which is it?
So who wins this cosmic fight? Well, it turns out that the effect from general relativity, the weaker gravity, is stronger. And when you run the numbers, the final result is that the atomic clocks on the GPS satellites actually run faster than our clocks here on the ground. They ban about 38 microseconds every single day.
Now, 38 microseconds. That sounds like nothing, right? But hey, remember what we said earlier about tiny errors?
If engineers didn't correct for this tiny relativistic time warp would cause a navigation error that adds up to about 10 kilometers a day. Your GPS would be totally useless within a couple of hours. So the system is designed to constantly, second by second, correct for this. Which means every time you look up directions, you're literally using a real-world proof of Einstein's theory of relativity. How cool is that?
So we've got the basic physics, we've got the insane timing, and we even have Einstein's relativity in the mix. Let's bring all this amazing science back down to Earth and look at the actual system that makes it all possible and just how much it's changed our world.
Basically, the whole thing works in three main parts. First, you've got the space segment. That's the constellation of about 30 or so satellites orbiting the Earth. Then you've got the control segment on the ground. Think of this as the system's brain, a bunch of monitoring stations that keep an eye on the satellites and make sure their clocks are perfectly in sync. And last, there's the user segment. And that's you. It's your phone, your car, any device that's listening for those signals and crunching the numbers.
Now, it's not a perfect system, you know? The signals can slow down just a little bit when they travel through our atmosphere. And if you're in a big city, they can bounce off tall buildings before they get to you. That's called multipath error. Even the satellites themselves can have tiny little drifts in their orbits or their clocks. But the amazing thing is, the system is engineered to know about all these potential problems and correct for them on the fly.
And the result of all this mind-bending physics and brilliant engineering? It's a technology that has completely, fundamentally changed our world. It's so much more than just finding the nearest coffee shop. GPS is what guides our airplanes and container ships. It helps farmers be incredibly precise, which helps feed the world. Scientists even use it to monitor earthquakes and track climate change. It's become this invisible, essential utility that pretty much powers all of modern life.
So we've gone on this huge journey through space, time, and Einstein's brain. What's the big takeaway from all of this?
I think it's this. The next time you glance down at that little blue dot, just take a second to remember what you're really looking at. It's not just a place on a map. It's the speed of light. It's clever geometry. It's the mind-boggling precision of atomic clocks. And it's a daily, real-world confirmation of Einstein's theories about the very fabric of space-time. All of it working seamlessly together, right there in the palm of your hand.
You know, this technology basically solved one of humanity's oldest questions. Where am I? It gave us a sense of our place in the world that was impossible before. But the story isn't over. As GPS gets woven into AI and things like self-driving cars, the next big question isn't just about knowing where we are. It's about predicting where we're going. So I'll leave you with this to think about. What does our world look like when our technology knows not just where we are, but where all of us are headed next?